All right, so we are going to start our first video for AP Chemistry, starting in Unit 1. And what we'll do is I'll have videos, and those videos will cover the notes that are listed in Schoology. I have the notes that you'll have. And what you'll need to do is watch the video with the notes handy, maybe on a split screen or something like that. And then whatever I put in this video, additional to what's in the notes, you'll need to make sure that you write those down as part of your notes. If you want to print the notes out and keep them in a binder, that would be a great idea too. Or if you just want to keep them all digitally, that's fine as well. You can just type on it's a Word document, so you can type on there and add what you need to add to it. So that's how this is going to work. I'll go over the PowerPoint in this lecture video, and then you'll need to put any additional comments that I make into those notes. Okay. All right, then let's get started. All right, so of the first unit, a lot of it is going to be review. There should be a lot of things in here that you should have done in pre-AP chemistry. So first off, we're going to talk about the mole concept, and then percent composition, empirical formula, molecular formula, composition of the mixture, electron configuration. All of that I feel confident that you probably did in pre-AP chemistry. Periodic trends, you probably covered that in pre-AP as well. Mass spectrometry and PES might be new for you. It's not a real common topic to talk about in most chemistry classes, so that might be new, but we'll go through that. And it's not too difficult. So this first unit should be a lot of review. Okay. All right, moving along. So the mole, if you think back to last year, mole is a pretty big deal. What the mole does is it connects how many atoms or molecules there are of a compound with its mass in grams. So if you look over here on the side, we just kind of have, it's like a bridge. You can take moles and you can go and find out how many particles there are in a particular compound, You can find out how many grams there are for so many moles. You can find out how many liters. So it just kind of bridges that gap and allows us to convert from one thing to the other. So it's connected to the number of particles, Avogadro's number, that's the 6.02 times 10 to the 23rd. It connects to grams, that's going to be our atomic weight, our atomic mass, or our molecular mass. And then it also connects to volume in the form of molarity and in the form when we do ideal gas law. So just remember that it's extremely important in unit conversions, and we'll be going back over those a lot. That's another thing I feel sure you probably did in pre-AP chemistry is unit conversions, or dimensional analysis is what we called it. So we're going to be doing that a lot again. Okay. So using the mole, let's see, why can't I find my pen? Let's see. Here's my pen. I'll have to use it this way. Okay. So using the mole, again, it can be used to find percent composition. And remember, percent composition, that just means the part of something divided by the total. Over time, my handwriting will get better. It's been a long time since I've done this. So percent composition, it takes a particular part of that compound and its mass divided by the total mass of the compound. So we're going to take the molecular mass of each element and divide it by the total mass of the entire compound. That's percent composition. Empirical formula is when we have the percent composition, we just find the simplest whole number ratio of elements in that particular compound. So like sugar is C6H12O6, and we can reduce that down to CH2O. And that will be the end of this particular video. All right, so this is part 2. I will have to upgrade my Screencastify. I can only do 5 minutes at a time right now, but maybe that's all we need to do 5 minutes at a time. So we left off at empirical formula. So we said empirical formula is the simplest whole number ratio um, of the elements in a compound. Comparing that to molecular formula, which molecular formula is the actual number of atoms in a compound. So it's the molecular mass, and we find that molecular mass by adding up the mass of all of the elements and atoms in that particular compound. So C6H12O6. That is a molecular formula. So there's actually 6 carbons, 12 hydrogens, and 6 oxygens. Whereas for empirical formula, that's the simplest whole number ratio, which that would be, which we wouldn't actually put the ones there. That would be CH2O. Okay. All right. Moving on. Percent composition. So when we talk about percent composition, remember we're going to take the total molar mass, total molecular mass of that particular compound, and we're going to divide that into the mass of each element that's in that particular compound. So you can see a sample problem here. There we go. All right, so we have KMnO4, which has a molar mass of 158 grams. Remember, we get that just by adding the atomic mass of the potassium, the manganese, and 4 oxygens. That's where those numbers came from. And you can see that down here. And then, so to find the percent composition, we're going to take the mass of the potassium and divide it by 158, and that gives us a percent, 24.7%. Remember, this is based on the law of definite proportions, which says that the ratio of the mass of constituent elements in any pure sample is always going to be the same. So potassium permanganate, KMnO4, is always KMnO4. It's always going to be 24% potassium, 34%, 0.8% manganese, and 40.5% oxygen. Okay, so definite proportions says the ratio of the mass of the elements in any pure sample is always the same. Compounds can be molecules or formulas. So they're formula units. There are 2 ways of saying the same thing. So a compound is a molecule, and molecules are usually made up of nonmetals that are covalently bonded. Or we can, if it's ionically bonded, we don't call that a molecule, we call it a formula unit. Both of them are compounds. So some examples, I'll use sugar again. I've been teaching biology for a little while, so sugar is a good example. C6H12O6 is sugar molecule. That is a molecular compound. It's a molecule because those are non-polar bonds there. Non-metals. Ionic would be salt, NaCl. That is an ionic bond. And so we would call that a formula unit. We wouldn't call it a molecule of salt. Okay? All right, moving along. Here are empirical formulas, and this is just how we determine the empirical formula, how we determine the smallest whole number ratio. First, we need the percent composition. So what we're going to do is, remember, we are always going to go the percent to the mass to the mole, and then divide the smallest number of moles into all the other moles that are there. Okay, so for example, calcium hydroxide, we have 13.5 grams of calcium divided by the atomic or the mass to mole ratio. So 13.5 grams of calcium, I know that in 1 mole of calcium, there's 40.1 grams. And so that gives me 3.37 moles of calcium. I do the same for my oxygen. 10.8 grams of oxygen. There's my mass to moles for oxygen, which gives me 6.75 moles of oxygen. And then hydrogen, do the same thing, gives me 0.668 moles of hydrogen. I take all 3 of those mole numbers and I divide them by the smallest number of moles, which is 0.3. Okay, so we left off talking about empirical formulas, how to get the smallest whole number ratio. And we said we divide the each mole amount of each element by the smallest molar amount, and that gives us our whole number ratio here. Remember that we always assume, if they don't tell us the total number of grams, we always assume that it's 100, and that's how we can get this. So we would assume that this is calcium hydroxide, and so that would be 13.5% calcium, which would mean 13.5 grams if we assume 100 grams. So if they don't tell you in the problem the total number of grams of that particular compound that you have, just always assume that it's 100, and that way you can use your percent composition. They'll give you one of the two. Okay. All right, so the next thing we're going to look at is molecular formulas. And like I said, we're going to be doing tons and tons of practice problems on these. And these videos are just like 5 minutes at a time. So we're going to watch them, and then we're going to be doing some practice problems too. So seems like a lot that might be thrown at you, but you will get lots of practice in doing it. Okay, so let's move to molecular formulas and talk about those. All right, so in a molecular formula, we are looking for the actual amount, the actual number of moles or actual number of atoms in that particular compound. So it says, what's the molecular formula for a compound which has an empirical formula of CH4N? So remember, the empirical formula is the smallest whole number ratio. And what we're given is the molecular mass. We know its total number of grams for the entire compound. So we know the smallest whole number ratio. So then we can determine its molecular formula. So we're going to determine the formula mass, and the formula mass is just the mass of the empirical formula. Okay, so we have one carbon, so that's 12.01. We have 4 hydrogens, that's 4.0. And remember, these are atomic masses off the periodic table. And we have 1 nitrogen, which is 14.01. So when I add all of that up, it gives me the total for the empirical formula. Then I'm going to compare, all right, that's my empirical formula. I'm going to compare that to my actual molecular mass. Okay, so if I do that, I can see that my molecular mass is 60.12, but my empirical formula, formula mass, is 30.06. So when I do that, that's twice the size. Okay, so 30.06 divided into 60.12 is 2. So all that I need to do is take that number and multiply that number by my empirical formula. Okay, so 2 times 1 is 2, 2 times 4 is 8, and 2 times 1 is 2. So my molecular formula for this compound is C2H8N2. Okay, so for that, first you get your molecular mass, you find your formula mass, you divide divide the smaller one into the bigger one, divide the formula mass into the molecular mass, and then multiply that whole number, by the actual empirical formula. Okay. Composition of mixtures. This should be pretty self-explanatory as well. Mixtures contain molecules or formula units of 2 different types in varying proportions. So they're not things that are chemically bound together. It's 2 separate chemicals together in different proportions. Okay, elemental analysis can be used to determine the relative numbers of atoms in a substance and to determine its purity. So you can look and see how many different elements or how many different compounds are in a mixture, and that can help us determine its purity. So, all right, I think that's going to be a good place to stop for this video. Yeah. All right, that's it for that. Okay, so this will be a practice video. We're going to look at how to determine the mole ratio. So these are just practice problems that we're going to work on in this one video. Okay. Okay. So our problem is sample of carbonate rock is mixed with calcium carbonate and magnesium carbonate. The rock is analyzed in the laboratory. So this is an example of a mixture. Like we were talking about compositions of mixtures in the last video. So the rock is analyzed in a laboratory and the results are recorded in the table below. Calculate the mole ratio of calcium to magnesium in the rock. Okay, so here's the total mass of the sample, 98.5. Here's the mass of carbon, the mass of magnesium, the mass of calcium, and then the molar mass of each one of those things. Remember, molar mass is grams per mole. So it's how many grams are in one mole, which is basically just your atomic mass. If you look, that's how they get that off of the periodic table. Um, so then what they're going to do next is they're going to take the mass of magnesium, okay, and find out how many moles of magnesium we have. So remember we said at the very beginning, moles is a way to bridge the gap from grams to moles, or to number of molecules. Okay, so we're going to take 2.4 grams. We're going to divide it by the atomic mass of magnesium, which is 24.3, which gives us the number of moles of being 0.100 moles of magnesium. And then we're going to do the same thing for calcium. So 36.1 grams of calcium divided by 40.1, which again, we just get that off the periodic table, and that gives us 0.9 moles of calcium. And then since it specifically says the mole ratio of calcium to magnesium, I'm just going to make a ratio of those two numbers. That's all I'm going to do. So 0.9 moles of calcium is going to go on top. That's the first one that's mentioned in our ratio. And 0.1 is going to go on the bottom. So it's a 9-to-1 ratio of calcium to magnesium. That means in that mixture of that rock, I have 9 times more calcium than I do magnesium. So that's an example of composition of a mixture. You have two compounds in there. They are two separate compounds, but they're mixed in varying proportions. And we just found the proportion for that particular sample. Okay. So again, should all be reviewed. And going back to the mole and that concept of the mole being extremely important for going between and converting between the number of particles, the number of atoms, between grams, on all of that is done through that concept of the mole. The molar mass, remember, is just the mass in one mole, and that's found, if you're talking about an element, that's found on the periodic table. If we're talking about a compound, that's found by adding up all of the atomic masses for each atom in that particular compound. Okay. So the next set of slides, we're going to start talking about atomic structure. A lot of this should be reviewed as well, but we'll be getting a little more in depth with some things in this next section. Okay. All right. If you have any questions, make sure you email me or contact me through Schoology, or just bring those questions to class with you and we'll get them answered for you. Okay. Have a great night.